Welcome. In this session in linear data analysis, we'll briefly explore how we can assess a linear regression, and we'll explore a couple of extensions to linear regression. So, to assess regression, we use the same measure of residual error that was minimized. So this is an important point, is that to assess, the only fair way to assess a method is to examine the thing that it was trying to solve. That is, where it may be an intellectual error to try to assess a regression on something that it wasn't trying to do. It's sort of like, how is it that we grade students sometimes on a hidden rubric, right? Well, we don't want to do that hidden rubric trick. So what we'll do is we'll assess our regressions using the same method. And this is typically it's called the root mean square, or RMS error. And in some contexts it's sometimes written as RMSE. And we'll say that the root mean square error, so what's that error of? Well, what was our model? Our model required the independent observations and required the dependent observations and used the parameters of our model. And in our case, the way that we'll do that is we were trying to minimize the sum of the squares of the error, and for statistical reasons, the sum of the squares of the error will increase infinitely if we increase the number of observations. So we have to correct for the number of observations. And the way that that's usually done is we'll take error 1 squared plus error 2 squared, and so on until we have the errors of all of the data. And we'll take those and then we'll divide those by the number of observations that we have. So that is this is the squared error. Divide by the number of observations, that's the mean squared error. And then the root of that puts it back so that the errors are in the same measurement coordinates that the dependent values were in. And this is sometimes written as the square of the error for the parameters that we have divided by the square root of the number of observations. Those are the same way. Now let's observe. So let's say usually, and we're going to explore this in a subsequent session in much greater detail. Usually, we'll say use all the data. Now, that may be methodologically dubious. That is, why should we use all of the data to evaluate a method? Could we perhaps use part of the data to find our W and then another part of the data to test? And that is a very rich concept that will take multiple sessions to explore later on. So now, let's switch and let's examine a couple of the assumptions that underlie linear regression. One of the key assumptions of all of our linear regression so far is that there are two kinds of data. There are some independent observations and there are some dependent observations. Well, what if all of the data are independent? And that can arise in many experimental contexts. That is a change of assumption. And when we have a change of assumption, we need a change of our model. So in that case, it turns out that what we perceive as linear regression instead becomes explanation. And the explanation in the context of linear data analysis is PCA, or principal components analysis. How old is this concept? Well, it dates back to 1901 by the famous mathematician and statistician Karl Pearson. And in one of his foundational papers, we can find this diagram. And here, he is writing out exactly this situation of what if the data are independent. And in that case, instead of having the vertical error, which is the error that we want in a regression, he's saying, what can we do for the orthogonal error, which is orthogonal linear regression? And he proposes then that we could perform these measurements and we could have an explanation which is not the same as linear regression. Later in the paper, he has this beautiful diagram. And here you can see he has X here and Y down here, which we recognize as being a left-handed coordinate frame. So at this time, the right-handed coordinate frame was far from universally accepted. And then he has a bunch of data here, and what he's drawing are three lines. Here is the regression where you model Y as a function of X. But if these data are independent, couldn't you equally well pick X as a function of Y, and you would get a different regression? And what Pearson proposed instead was that you have a line of mutual regression, which is principal components analysis. And he wants to do all of the analysis around C, which he calls the centroid, and we would call the mean of the data. So these ideas date back to Karl Pearson, and it took a long time for people to fully understand the implications of his suggestions. Now, another question which arises all the time in linear regression is what happens if our data are linearly independent but not orthogonal? And for linear regression, we're viewing it as a projection problem. And what that means is we're trying to take the dependent observations C and as a vector, and we're trying to project those into the column space of the matrix of independent observations. And when we do that projection, we want to get some vector P that is in that column space. Well, this requires, if we're going to find P explicitly, then we know from previous sessions that this involves inverting this matrix. Now, we know that if the data in A are linearly independent, then A transpose A is symmetric and positive definite, so it's mathematically invertible. A practical problem is that it's often ill-conditioned. And by ill-conditioning, what we mean is if we go back to our original data matrix, up here, go to our original data matrix, and we take the SVD, we find that the ratio of the first singular value and the singular value that denotes the rank, which is usually n for n columns, that this is a very large number. And so when we have ill-conditioned data, this projection is numerically dubious. It can give us some quite erroneous results. And one solution that we could have for data that are not orthogonal but are linearly independent is, can we compute an orthogonal basis, actually even better is an orthonormal basis, of the column space of the matrix that we're given? What have we learned in this lecture? Well, we're now able to solve linear regression using the normal equation for projection. We know how to use zero-mean data in linear regression. We can use standardized data in linear regression. And we know how to find the error of a linear regression and evaluate or assess our linear regression by the root mean square error.